Hello, this is Professor Elliott, and this short video lesson we will talk about diode rectifiers. Okay, the first circuit we're going to look at is the half-wave rectifier. So you can see that we have a single diode on the secondary side. Oops, my pen here. Okay, so a half-wave rectifier has a single diode with the direction of the diode shown. You'll always get a positive output. And just sort of an FYI, if you were to turn the diode around and put it this way, that would give you a negative output, which would simply look like just a mirror image of the waveform below. But anyway, so the current flowing through the secondary can only forward bias the diode when this point here on the transformer secondary is more positive than the cathode, and then current using conventional flow is going to flow that way, and then down through the load. So we calculate the peak secondary voltage right there, okay, and then the output voltage is simply the secondary voltage minus the 0.07 for the diode drop. The average output is going to be the output peak times 0.318. And if you look at my professor notes, all of this is detailed there as well, so this will kind of go along with that. So the output voltage is often called the average voltage. So the average and the output voltage are the same, and this is the DC voltage that your digital multimeter will read. And in my simulation here, you can see we're comparing the input voltage on the secondary with the output voltage, and that's basically how a half-wave works. Okay, this is going to be called the full wave rectifier. You'll notice that the difference in the output, whereby the output one of the diodes is always conducting. Okay, you'll notice that we're using it's called a center tap transformer secondary, where the center terminal is tied to ground. That's very important. So the way this works is that for half the AC cycle, current is going to flow that way because D1 is forward biased, and then for the other half cycle, current's going to go this way because D2 is forward biased. So for half the cycle, D1 conducts and D2 is off. For the other half cycle, D2 conducts and D1 is off. And because of that, we have a full wave output. And because the output is always conducting, then the average voltage voltage is going to be twice 0.318, which is 0.636 times the peak output voltage. And again, if you want all the formulas, just look in my professor notes, and you'll find that all detailed there for you with examples and everything shown. So anyway, so the disadvantage of this arrangement versus the bridge rectifier, which we're going to look at briefly next, is that you need a more expensive center tap transformer, but otherwise the output waveform has the same shape. And because of the one diode is always conducting, the output frequency is always twice the input. So in this case, if we're putting in 60 hertz, that means then we have 120 hertz out over here. And if we go back to the full wave, so the half wave, sorry, we have 60 hertz here. That means then the output frequency is 60. Okay, so All right, so that's just the quickie overview of the full wave rectifier. And then finally the bridge. And for this bridge, I've added in what's called a surge resistor. And this is often used to limit the current through the diode bridge. When we first power up the rectifier, so the surge current demanded by the capacitor doesn't exceed the maximum current rating of the diodes. So anyway, so because we have 4 diodes, 2 pairs are conducting at a time, and the output looks essentially the same, or it is the same as the full wave. Okay, and we have the output's going to be like that. Now, because we have the capacitor, so the capacitor changes the output slightly. So we're going to look on the next slide. So without the capacitor, then the waveform will actually go down to 0. Once we add the capacitor in, and that's called the filter or filtering capacitor filter, then you notice how the 0 is down here, but the whole waveform has been shifted upwards. So this is known as the ripple, and the ripple is basically that there, and more specifically the peak-to-peak ripple, which is how it's normally expressed, is that difference there. And that is really just the charging and discharging of the capacitor. Notice how the DC voltage is much higher because the capacitor prevents the output from going all the way down to 0. So with the filter capacitor, you're going to have a higher output voltage and a much smoother level DC. And if you go back to here, you can see this is not this is DC. It's technically, we could call it pulsating DC. It's not very smooth yet. Once we add in the capacitor filter, then the output is much smoother. So anyway, so we'll follow up with this in class. Do take a look at my notes, and there's sample problems in my handout, and that should get you prepared for next class. Okay, great. Thanks for joining me, and we'll catch you all soon. Cheers. Bye-bye.